In our last two videos, we've talked about the difference between linear function and a nonlinear function and their constant rate of change. And so I have these two word problems that we're going to work through and how we can continue a table based on information. So our first one, when a scuba diver goes, underwater, the weight of the water puts pressure on the diver. The table shows how the water pressure on the diver increases as the diver's depth increases. Now, this is asking us what is the rate of change of this linear function. So we know it's a linear function. So from here, we just have to find, given 2 points, that rate of change. And so that is easier by just working with the first 2 points because those are our smallest. So if we do 8.8 minus 4.4, we're going to get 4.4. And 20 minus 10 gives us 10. And so our rate of change is going to be 4.4 over 10. And so what does this rate of change represent? Well, this rate of change represents that for every 10 feet we dive, 4.4 pounds per square inch in pressure we increase. So for every 10 feet we dive, we increase by 4.4 pounds per square inch of pressure. So every 10 feet we go down, 4.4 pounds per square inch of pressure is added on. Or there's 4.4 pounds per square inch of pressure for every 10 feet we dive. And so either way that that's worded, that's how we would come about it. Now, part B is asking us to use the rate of change to predict the water pressure on a diver at a depth of 60 feet and of 100. And so the best way to do this is just increase or continue our table. And I'm going to try to draw. So here's 40, so this one would be 50, 60, 70, 80, 90, and we're going to barely fit 100 in here. And of course my table lines are not the best, but it is what it is. And so I'm going to start with the 17.6. And I'm going to add 4.4. And so when I do that, I get 22. And then I'm going to do 22 plus 4.4, and I get 26.4. And so for 60 feet, our depth is our pressure is 26.4 pounds per square inch. Add another 4.4, we end up with 30.8. Add another 4.4 and we get 35.2. Add another 4.4 and we've now got 39.6. Add another 4.4 and we end up with 44. And so that brings us to 100. So for 100 feet, we are dealing with 44 pounds per square inch. And so we just extended our table using the fact that we knew that we add 4.4 to each of our y values for every 10. And so I added 10 to each of these, and I added 4.4 to each of my y's. So now let's move on to example 5. So suppose there are 20 rabbits on an island and that the rabbit population can triple every 6 months. So we're going to make a table of values to find how many rabbits there would be after 2 years. So our x is going to be, I'm going to call it months. I know it wants years, but I think it's easier to start with in months and go every 6 months. And then this will be rabbits. And so after 0 months, because we're starting with 20, right? So 0 months, we have 20 rabbits. After 6 months, we're going to take that 20 times 3. And so now we have 60 rabbits. After 12 months, so a year, we're going to take that 60 times 3, and we now have 180 rabbits. After another 6 months, so at 18 months, we take that 180 times 3, and we now have 540 rabbits. And then in another 6 months, so in 24 months, which is 2 years, we take the 540 times 3 and we get 1620. And so make a table of values to find how many rabbits there would be after 2 years. So after 2 years, there would be 1,620 rabbits. And then it says, does this relationship represent a nonlinear function, and explain? Well, we need a constant rate of change to be linear. So if I do 60 minus 20, I end up with 40. And 6 minus 0 is 6. But if I do 180 minus 60, I get 120, with 12 minus 6 being 6. And so this is not a constant rate of change. And so does it represent a nonlinear? Yes. And the reason is because there is no constant rate of change. And so that tells us that it is a nonlinear. Now we're going to use the table, and when would we expect the rabbit population to reach, is that 1,000,000 rabbits, right? 1,000, yep, million. So I'm going to take that 1620 times 3, and now I am at 4,860. I'm going to take that times 3, and we're now at 14,580. So, well, that would have been 24 plus 6, which is 30 months, and then 30 plus 6, which is 36. We're going to take that 14,580 times 3, and we get 437, or 43,740 rabbits. Helps if I could talk. And then 36 plus 6 is 42. We're going to take that number times 3, and we've now got 131,220. So we haven't quite reached the million. And so that is after 48 months. Take that one times 3, and we end up with, what, 393,660. And so then we add 6 to our 48, and we get, no, go back, 52, and, nope, 54, sorry about that. And then I'm going to take that 393,660 times 3. Now we now have, I'm going to write it over here, 1180980, and that is after, so 54 plus 6, 60 months. And so in 5 years, because 60 months equals 5 years, that's when we get the over 1,000,000 rabbits. So in 5 years. And I guess it'd be in about 5 years, because we go over the 1,000,000. Now, does this taking into account their predators, or no? This is just us guessing, knowing what we know about their population, that after 5 years there would be this many bunnies, and that is a lot of rabbits. So again, this is nonlinear. Even though we were multiplying by the same number every time, it does not create what would be this is actually what we call an exponential function, because it grows so rapidly. So until next time.